robots doing a complex task in a simplified environment, but have robots starting with a simple task in a complex environment.
So we're Team Tech United. We participate in the RoboCup at Home League. And this league is about robots doing a course in a household, obviously. The robot has to be able to do a lot of things in a household. So today we already tested the navigation skills, the speech recognition skills, the person recognition skills. And tomorrow we will proceed by object recognition, object manipulation, following a person through an unknown space. So we will guide the robot actually throughout the whole venue, and then it must be able to find its way back on its own. In the future, I think it's really useful to have these robots in the real world, although it will take some time until they're at the level that they're actually useful. And now we have to teach them the environment, teach them the objects, teach them the people, and that all
Zo, Jurgen, je bent er al. Ja. Hè? Ja, precies. Ja, precies. Ik zag hem. Ik zal even de applicatie delen waar de dingen in zitten. De score sheet. Ook al. Dan ik doe vanaf. Wat zeg je? Een huiskamer waar straks. Normaal zit ik boven, ja, dat klopt. Een beetje in de gaten houden hier. Er zijn nog wat kids die moeten studeren. Share my screen. No, I don't like to share my screen. I like to share my application. Go live.
Hi everyone, from 3 minutes later, ASML and Falcons will start the scientific challenge. If you are ready, please move to the competition room. Thank you.
Recording in progress.
Okay. We still have several team leaders not here. I think I didn't see a team leader from the Iris. They also there are also no team members in the open room. I suggest we can wait for them maybe 1 minute. Thank you. Okay, good morning, good afternoon, maybe good evening, everyone. Welcome to Middlesex League. Tonight we will have our scientific challenge, and we have some teams here, and we will start from the Falcons. Team Falcons, can you hear me?
Yeah, we can hear you fine.
So if I'm ready, we will start the challenge for you.
Yeah.
Okay, I will stop share my screen, and it's your time.
Okay. Okay, thanks.
Yeah. So hello everyone, I'm André Pol from the Falcons ASML, the Netherlands. I want to talk to you today about the vision stuff we are doing. In the past we had a simple system with state machines and color recognition, and we did now some investigation for machine learning. And my presentation is consisting of 3 parts. First about the algorithm, then a proof of concept, call it a quick hack to check the feasibility, and then the last part is about the integration. I think I don't have a lot of time, so already my excuse is that we'll run out of time and maybe we have to skip some parts. But I think the most important things are in the beginning, which is actually also a kind of a recap of the workshop in December. Then I also showed some stuff, but in the meantime, some things have been updated. So I hope it all makes sense. So my first question is why machine learning? So this is a part of the configuration stuff I have for the current system. So there's a lot of sliders. So when it's mainly about light condition changes. So first I have to set the white balance correct. I have to set the gains correct and all kinds of stuff. So it's pretty labor intensive, and that doesn't make things very easy. So that's my main thing. I want to change it. Furthermore, the current system is also not really suitable for real good improvements, like if you want to do black and white balls and stuff like that, or obstacles of arbitrary space. And another big thing is because we can do something special, we want to do it. So that's the reason we want to investigate the machine learning stuff. I did a lot of reading on the internet about it, but a lot of people always end up with this YOLO stuff. So that's the way that's the part I investigated in. I looked at. So I didn't look at the other stuff, but I think there's something which is really a lot better than this. And so that's the main thing. I'm not gonna do the details about this YOLO stuff because you can find it out yourself. What we want to do is we want to detect with this YOLO, want to do the balls, obstacles, human, and goalpost and border. And the human, goalpost and border, that's the new stuff which we currently do not have in our current system. What we don't use, what we're not planning to use the machine learning for is the line detection, the localization. And the main reason is that's already working pretty well, and we don't expect it will be more accurate in centimeters, I mean, than doing this with this machine learning stuff. An important thing of this this YOLO stuff is it's heavily relying on this NVIDIA CUDA GPUs, so you need a lot of those to get it already. It started in 2015 by Joseph Redmond, and currently he's not in anymore, but is now now maintained on the internet, and the main developer is Alex of Bochnovskiv. I don't know the name, or I pronounce it correctly. He's from Moscow, and there's a lot of people working on it, and it's really active, maintained. To test it, you need, of course, stuff to learn. So what I did, I just looked through our database of all the pictures, and I sorted about 1,300 images which are relevant. I put them in there and annotated them. So that's a lot of labor work, but yeah, it pays off in the end. In the end, I want to crank this up to about 10,000. So that's something I was reading about. You need for real good stuff, real good performance, you should go like 10,000 or more. And I'm running a full YOLO 4 network. And I only have currently I only have 5 classes. Later we probably want to extend it. So maybe we want to be able to know if it's our own robot or an opponent, like if it's a robot from Tech United or Gambada or whatever. And we scale the images down to 416 times 416 pixels. That's not a lot, but the reason is if you make real big pictures, then it will eat a lot more GPU power, and it will really become difficult to run it on a robot. Another interesting fact is the weight file. So after training, or the thing that's configuring the network, that's like 245 megabytes. So if I don't know exactly what types to use, but if they use 32-bit floats, that would mean there are 64 million parameters in a network that are configured. So that's really a lot to get going. About training stuff, when I started with this YOLO first version, I think it was version 3 something. It took about 2 weeks to get it trained, but now at the later YOLO 4s, that's somehow they optimized stuff. I don't know the details, but now after 2 days, if I start from scratch, in 2 days I have a reasonable running there, and I run it also on an RTX 2080, which is overclocked at 2 gigahertz, which is actually pretty awesome card. So the question is, does it work? And look for yourself for the images. In the left images, you see this ball there, which is really only a fraction is visible through this other robot, but it's recognized. And on the right, you can see we see all these optical balls and humans, so it's very nice. And the question, where's the ball? So it's pretty hard to see it, but I hope you spotted it in time. So it's just in front of Bernardo's feet. So it really works. I cannot say anything. I don't need to add a lot of it. The pictures are speaking for themselves. One nice feature we added is the goalpost. So the reason for that is we have localization, and it should be pretty accurate, but we could be a few degrees off an angle, and in that case, you just could shoot next to the goal. So if we know the goalpost, then the exact location, it doesn't matter so much anymore. We just know, okay, we want to shoot, where's the goal? And we know then exactly where the goal is, and we can aim pretty accurate. So we hope that will improve our shooting accuracy. Also, I did some look at the very bad light conditions. So this is really bad. I never would play, I accept this as a normal field, but we can also, actually the algorithm also works over there. It misses then, and the left is also an object. It doesn't see that one, but I'm already really surprised that it sees this ball and this obstacle in this picture. Some more stuff about YOLO. It also works for images with different aspect ratio. So yesterday you saw this little movie from Jan, where we did this human interaction with this with the playing stuff, and that's a different camera with a different aspect ratio, and that's also eating this stuff. And I have to resize it. So that also works. I mentioned already, I'm testing with full-blown YOLO. That requires a lot of power of GPU resource, and that means a lot of battery power, which is quite limited on the robot. I also tested with tiny YOLO that works for nice pictures, but as soon as you go to a kind of bad weather, then the performance drops significantly. So in the end, I expect, I'll save this optimization to the last. In the end, I expect we will somewhere probably end up in the middle, somewhere between a full-blown YOLO and a YOLO tiny. I tested this with YOLO 4, which is, I think, very nice. But there's already a newer version. It's called a scaled YOLO v4, but I didn't test that yet. Not yet. And I already mentioned I did not evaluate other algorithms because I was already flabbergasted by this one. So I'm really happy with it. Some last important things to mention is to integrate it with your own stuff. So this YOLO, that's the framework, that's the algorithm. But it's coming with darknet. That's the framework where you can build you can modify it or build your own code against it. But another nice feature is it's also compiled as a library. So you can just link it with your own code, and you don't need to bother so much anymore about building this darknet stuff. And to make it even more nicer is that some other guy from Canada create an additional layer and made a C++ library for it, where also you still need to do quite some stuff to get it working with the C interface stuff. And this guy from Canada also made it really simple that you only need a few lines to get it working with your code. And I tested that stuff, and it also works, so that's very nice. So the summary about machine learning for this vision stuff, I think it's a full go. It's very nice. And for me, I'm really happy about it, because normally at tournaments, I have to spend a lot of time in tuning. And now I can just do some more coffee drinking or whatever, because I don't need to do the tuning anymore. Next phase, the proof of concept. So yeah, this is all theoretically with JPEGs and stuff, but does it really work on a robot? And for me, that's important, such kind of test to do that, because normally we think something on paper, and then we try it out and we miss stuff, and then it doesn't work, of course. And to do a full-blown test, that really helps us to get it going and find early things we missed somewhere. So the idea is just crank it on an existing robot. Don't change the robot. Just keep it as much as possible as it is, because we still have to use that for our normal testing stuff. And just try to get it going, but we don't look at performance. So really bad performance, we don't care. It just is a functional test to check out if the complete flow is working. And for that, I just took a little older HP notebook laptop we had around, which has 640 CUDA cores. So that's really low compared to these normal GPU cards. And I created some visualization tools to do some diagnostics and to know what's going on. And in the past I used always the stuff from OpenCV for that, but I now moved to the Qt because there was some limitations in there with the slider stuff in OpenCV. So this is a picture about the flow, the normal flow is. So at the left you see the cameras, the 4 Raspberry Pi cameras going to 4 Raspberry Pi boards. In these boards there's the color filtering running and the state machines are running there, related to all the sliders I showed in one of the first slides. And then these color filters spit out object vectors. They're going to the CPU box, which is in the right corner. And there these objects get extracted and they get dewarped. Dewarp means converting pixels to meters and angles. So that's from the camera pixel coordinates to the real world to the meter coordinates, this stuff, Cartesian. And then it's going to the world model thingy. And next to the object stuff, we have also a dewarp with localization, which is used to find out where we are. So in this test, and there's also next to this object vectors, we also have a debug stream with data going from this Raspberry Pi cameras to the CPU box. And in this debug stream, there's also JPEGs, and the plan of the ID just hook up to the JPEG stream. So now we get this JPEG stream. This is all on Ethernet. So I have just this laptop is connected with Ethernet to the CPU or to this network, and then I just hook up to this JPEG stream and feed it to YOLO darknet. And YOLO darknet out of the box is able to accept different formats, like it can have MPEG, it can have webcams, and it can also support MJPEG as input. So I created a block that converts the JPEGs to an MJPEG streamer, so pretty straightforward, and I feed it into the YOLO, and YOLO is able to spit out the objects in different formats, and I took the JSON one, and then I have the JSON decoder that just eats out the information from
10 minutes.
Okay. I'll wrap up. So then this is fed back to this adapter and then going to the world model back, and then we replaced the normal dewarp thingy there. So this is the image there. So this is this is what the debug shows. In the left lower corner, you see this what darknet is spitting out, and in the right there's the dewarped version, and it's the top view. So you should clearly see the ball in like 6 meters in the left corner, and at the right you see the obstacle. So I did some real world tests. So there it is connected. The laptop is connected to the robot, and there you see it all going. I had a short movie. I'll show you a little part of it. It's really nice. So this is a real test there, and it might not look so fancy at all. It's not performing that well, but the idea is that it's a full cycle. Everything is in there. So it's actually now using this machine learning stuff to see where the ball is in it, and it's going there. We're lucky. There we go. So first, this is a major milestone because it's actually showing that the complete concept is working. So yeah, that's the main part. So I had more stuff about the integration, but that's for another time then. So that's the next phase what we could do. Thank you for your time.
Thank you. Questions, please.
I have one question, maybe, if I may. Can you hear me?
Yes, I can.
Okay, sorry. Andre, you said you convert quickly to YOLO. Eh? Can you tell a little bit more about that? In comparison to the other alternative technologies, let's say.
No, I don't have a lot of information about it. I was reading about it, and most people come out to that, and that was for me a point to just start with that one and find out if that's working. So I don't have a lot of details about the other algorithms that are available.
Okay. Thank you. Maybe one more question for me, if that's okay.
It's fine with me.
Andre,
Yeah,
can you give Sorry?
No, it's okay.
Yeah, if someone else is, it's okay. I can.
Go on then.
My question would be, can you give an indication of, let's say, the frames per second performance that you achieve, Andre?
With this laptop, it's 4 frames per second.
Yeah.
But it's an old one, and it's comparable with like this Jetson board stuff. But we target for like 30 frames at least, and we hope actually for 40 frames per second. That's our goal. But then with 4 cameras. But then we need, of course, more GPU power, and that was the rest of another part of the presentation. We'll save that for the last. That we're gonna use a GPU card or a laptop with an embedded GPU in there, like a more recent one, like the Ampere series.
Okay. Thank you.
And so maybe another side note. So the frames per second, that's not the main thing. It's more the latency we because we could still have a lot of pipelining in there, and then we could have a frame rate like for like say, let's say 40 frames per second. But if we still have a latency of 200 milliseconds, then we still nowhere. So it's a combination. We hope for like 50 milliseconds somewhere in that range of latency, and then like 40 frames per second.
Okay. Thank you.
Okay, thank you very much. And I see Fernando raise his hand up. So Fernando, please.
Thank you very much. I myself have been working as well, a little bit as well with YOLO. And my question is, if you have over 1,000 images, but for each image, you need to say exactly where the things are, the ball, the humans, the obstacles. How do you do that for that data set? Do you use your traditional software to point where the ball is, where the human is, etc.? Or how do you give that information to YOLO?
I did both actually, but for this test real training set, I did all the labor work because I wanted to really be sure that it was correct. So it's a lot of work. It's labor work. But in the end, I'll think I will make some more automated stuff that I have some pre-selection. It's not only the annotation, but also to find the correct images, because a lot of images are pretty much the same because the robots don't move. So I really look for images which are interesting. So there's the ball in there, and it's on a specific things in there. So it's a lot of labor work. And you can they're on GitHub, so you can use them. I think VDL already uses them there. So if you want to load the link, just drop me a line. I'll share the link.
Okay, thanks.
Yes,
It should be going. If you have it, then you should be going in a couple of hours.
Okay, thank you. Could you please stop share the screen? I will share my screen.
Yes. So thank you very, very much all, and enjoy the other presentations.
Next
Thank you.
is Filipino Masashir. Please go to the competition room.
Okay, next team will be the Himikino. So team member from the Funcos, could you please leave the competition room, and maybe you can go back to the open room. Thank you. Thank you very much.
Next is Filipino Masashir. Please go.
TV Himito, are you ready?
Yes.
So Michael, maybe you need to mute one mic because they have an echo. TV Himito, I will stop share my screen, and it's your time. Thank you.
Can you see my slide?
Yes.
Thank you. So we would like to talk about the research on human-robot cooperative systems for our robot symbiotic systems. Our presenter is me, Moeko Tominaga, and our team is Hibiki no Musashi. The issue is how to try to cooperate with human and robot. So if humans and robots play circle with the same tactics, the robot's current communication technology cannot be used. So in the future, both human and robots will need to determine their actions based on the behavior of others. So without the Wi-Fi communication. So what's the problem? Now is human-robot interaction technology. Usually the command is by the gesture or the voice, and the behavioral decision based on explicitly presented triggers. So humans should do some gesture or say something. But in the future, maybe the robot have to feel the human's mood, and we have to the robot have to decide the next action. So this research aim is robot predict human behavior and decide the roles. So detail of the issue to be addressed, how to recognize the implicit behaviors of the others. Roles and the behaviors determine the implicitly. It means prediction based on experience, and also decision making based on shared tactics within a team, I think. And also what are the decision making factors is the location of the human, of the human or robot, and the goal, and the speed, and the direction. Also score we need maybe, and the elapsed time also very important, I think. So clarify the determinants of behavior by clustering the factors that determine what a human or a robot decides to do. So we will use the TensorSum for this. This is a clustering tool. If we use the TensorSum and develop this system, we will get the benefit like this kind of benefit. So how to use the clustering method for decision making? So this is TensorSum is a clustering tool, but if we input the state quantity and the behavior of others, behavior of others, so we can get the action. The action is the behavior. So the clustering tool TSUM can do this transfer. The clustering is a good point. This TensorSum's good point is visualize and map the situation in a clear way. Also, interpolation function. So we don't need input full situation in the game. The sum is a very old method, but I want to explain a little bit. The sum it can be the clustering tools, and from the real shape, real space to the future space, then we can get this future map. For example, if we learn some kind of the animals data, the dimension is around 20. In this case, we can get like this kind of future map. the feature map, please see our right side is maybe the bird. The left side is not bird. So this feature map can separate the bird or non-bird. And the extended sum is tensor sum. It means we use the tensor data, like this kind of tensor data. For example, if we use a tensor sum, the people and the drink and the situation, the people, which kind of drink they want. If we get this data, we can see this future map. So, for example, if the situation is desk work, and if the desk work do the young woman, in that case, young woman maybe like the cafe oreo or coffee. This kind of data is tensor data, and if we use like this kind of tensor data, we can use like this tensor sum. So if the situation change, the coloring change. So the color is red is high demand, the blue is low demand. And the experiment we did 2 experiments, and the working 1 experiment. First is human behavior using velocity vector, and second is robot behavior. So first experiment we use the human's data. The human is the professional of the futsal. And they play 5 versus 5. And the environment viewer is the player is red or blue. Depends on the team, and the ball is white. This line is the vector velocity vector. So this is a future map. If we input this kind of situation, we can get out of it this tensor sum future map. So input is like this situation, and output is almost the same positioning of the players. So we've succeeded in mapping the relationship between the player position and the output, the velocity vector. But when implemented in a robot, it's hard to determine the behavior from velocity vector alone. So we try to use the simulator of the robot, and using the simulator, we got the logging data of the RoboCup soccer, and then we use this kind of the behavior algorithm selection 1 to 7. This is our team's program, and we did like same kind of experiment. And this is the result. So now I show only 1 player and 2 player of 1 and player of 2, and the blue is train result. So at first we train the testers run this data, and after that for the judgment we put the testing data, and we try to compare with the input and the after running the output. We've succeeded, I think we've succeeded in the mapping of the relationship between the player position and output of the behavior algorithm selection. Maybe you can see the different action selected, but it's not bad because all of the player run 1 time. So this is good for our algorithm. And using the behavior algorithm selection, it is easier to implement in the robot. So conclusion, we try to learn the human's brain, the algorithm from the location and the state and the obstacle state, and the output is action. If we learn this algorithm, the robot also can trace the algorithm, and in that case, the robot can be the teammate of the human's team. So in the future, maybe we can collaborate with the robot and play with robot the soccer together. This is all. Thank you.
Thank you, Moiko. Any questions? Questions, please.
May I ask a question?
Yes, please.
Okay, this is Tom Pijnenburg from Robot Sports.
Yes.
So you gave a very nice example of let's say, starting to interpret the intention of another player.
Mhm.
If you look at the future, how do you see, what do we need to do to get a full observation of a human soccer player intention? How much work would you believe this is based on your the start that you have shown using your approach?
So at first we should observe the humans, the body language also. Yesterday we watched the Tech United the research, so we also have to learn about that kind of knowledge, and then also we have to search about the other field, the research. For example, already the soccer game, we can get the data from all over the world. So also we should use like that kind of data, I think. Then after that, we also have to get the humans, how to say, the tension and the motivation. Also, the human's behavior depends on the day's motivation. Also, the how to say, the fine or not good, the day's human's condition. So we also have to get the data from the human, but it's very difficult. So now I try to search about how to get that kind of data.
Okay, thank you.
Thank you very much.
Any questions, please? We have still have 1 minute. Any questions, please? So if no more questions, thank you, Moiko. Thank you very much. Thank you, Team Kindle. Could you please stop share your screen and I will share my screen. Thank you.
Thank you very much.
Next team is Iris. Team Iris. Team member of Heavy Kingdom, could you please leave the competition room? Thank you very much. Team Iris, are you ready?
Please move to the competition room, Iris.
Iris, can you hear me?
Yes, I hear you. Please wait. My team.
Sorry, there is a very loudly echo. Moiko, yes, thank you. Team Iris, can you hear me?
Check. Anyone can hear my voice?
Your voice is okay. Your voice is okay. So if you are ready. Okay, I see team members want to join the meeting room. Okay.
So in the middle of presentation, my friend will play the video.
Okay.
It is Krishna. Please pin him in the middle of presentation. That
I see a team member of your team raise his hand. You can, if you want to play video, you can open the camera. I can see.
Okay. Okay, we're ready now.
Okay, thank you. So we still have 2 minutes, so let me stop share my screen and then let me check which one you want to play the video.
No, I'll play the video in the middle of presentation. From now, I'll share screen my PowerPoint presentation.
Yes, you can, please.
Can I start the presentation now?
Yes, please.
Okay. Good afternoon and good evening, participants and everybody. For those who don't know me, my name is Puri Satriavi. I'm a member of IRIS from Institute Teknologi 10 November Indonesia. So hello, we're IRIS from Indonesia. IRIS is an acronym from Test Robot Intelligence System. It's a robotic team from 10 November Institute of Technology, focusing on autonomous soccer robots. Our team has 4 divisions. They are mechanic, electrical, programming, and official division. And I'm glad to inform you that one of our most significant achievement was winning Indonesian Robot Contest 2020 last year. And fun fact, it is our second time to win this competition in a row as a champion. KRI, or Contest Robot Indonesia, is an Indonesian robot contest that consists of several competitions. One of them, where it is participated, is Indonesian World Soccer Robot Contest. Okay, ladies and gentlemen, those are 2 pictures that depicting same event in 2 different years. First picture is KRI in 2019. In 2019, KRI was held offline, which was divided into regional competition and national competition held in Lombok and Semarang. This competition was held with a match system face-to-face between 2 teams. And the second picture is from KRI in 2020. In 2020, KRI was held online, which was divided into regional competition and national competition held at each campus. This competition was carried out with the new rules that I will elaborate in the next slide, and was held via online streaming with direct judges monitoring us. Okay, from that, let me go into some more detail about the rules. According to the rules, it only required 2 robots for running the sequence. There are 8 points of possible obstacle, and it will be randomized. First, the referee will randomize in the middle one between number 7 and number 8, and then randomize the rest. So there will be an obstacle in the middle, and there will be 2 obstacles in every session. Okay, from now, I'll explain more about the sequence. There is a starting point position for each robot, right side for R1 and left side for R2. According to the rules, first move, R1 will be the one who approaches the ball, doing calibration and takes the ball, while R2 is running to get in position himself and preparing to receive the ball. But the distance between R1 and R2 is not less than 1 meter according to the rules. After our robot are ready, R1 will pass the ball to R2, and as soon as possible, move forward to the next point position by considering the distance not less than 1 meter toward the goal. Then R2 will pass the ball to R1, and then R1 face the ball to face the goal, shoot the ball into the goal. After finish, R1 and R2 will come back to the starting point position. And The ball boy will place the ball back to its original position, and the sequence will repeat until the time's up for 3 minutes. What's interesting in this competition are the robot must not move when passing or receiving passes, and the ball must be perfectly catched by the receiver, or a minus point will be given. But the question is, how can we do that? It is because our robot has an additional camera installed on the front of the robot, and the tag number is attached with a different color for each robot. When the robot wants to passes, the robot will try to direct the camera to the tag number section by detecting the color using PID. After the process is confirmed, the robot will after the process is confirmed, the robot will pass the ball. And of course, our robot has been programmed, which has a condition to be ready to be passed or receive the ball. When this condition has been confirmed, the robot will pass or receive the ball without changing positions. And this is the highlight of Iris Champions at Indonesian Robot Contest. My friend Iris Krishna will play the video. Please, Mr. Velu, to pin him. Please raise your hand, Krishna.
Which one will appear the video? Okay, I see. Could you please wait a minute? Wait a minute. Okay, you can restart your video. Thank you.
Please pin my friend Iris Krishna.
I have already pinned the video of your team members.
Okay, Iris Krishna, please play the video. Yeah. This is the video from Iris. Okay. Thank you. I'll start screen my PowerPoint again. Okay, and this is our achievement of Iris Champions. We got the best design. We also got the best strategy in regional competition. Of course, we are champions at last one. Institute Technology School November was set to be the grand champions of Indonesian Robot Contest. From now, I'll explain more about the algorithm of collaboration that we use in this competition. The goal of this competition was to score as many goals as possible. We use a different technique of collaboration and decided to calibrate the position based on the ball. Besides the other team, most of all just using line calibration. Line calibration is a technique for initializing the robot's position based on the robot's position when it touches the bright line. This calibration can be set to be less than optimal and good enough because the condition for doing this is that the robot must touch the line, while the position of the line is on the edge of the field, so it will take additional time in one cycle to score a goal. We use the advantage of the ball being on the same spot every sequence. So the way we calibrate is based on the position of the ball. The ball is always at the kick-out spot every sequence at X ball 300 and Y ball 450. Before the robot grabs the ball, it will stop for a moment for calibration. We will use the fact that the ball is always at the spot for robot calibration. For example, if the robot's position now is X robot and Y robot, and the ball's position based on the robot's odometry is X ball 320 and Y ball 455. From that, we know that the ball is not in its right position, so the robot must be drifting. We can calculate the deficit of the real position and the vision position as X deficit 320 minus 300 equals to 20, and Y deficit 455 minus 450 equals to 5. So the real position of the robot now are accent, X robot minus 20, and Y robot minus 5. But the drawbacks of this calibration is the robot must stop to calibrate for the stability of the data. Nevertheless, it just takes a few seconds, so the ball calibration is much more effective than the line calibration in this competition. And this is about the result summary of this competition. In the first session, we got a high score with 20 goals in 3 minutes. Second session, we got a high score 2 with 20 goals in 3 minutes. And in the last session, we got a high score 2 with 19 goals in 3 minutes. Besides the other team, just 10 goals, 16, even more, just 6 points. And this is about the experimental result, about the percentage of successful passes of the team that participated in this competition. As we can see, the graphic is growing up. And how about the future challenge in RoboCup? What we did during the KRI, it is about basic soccer skills tasks, dribbling and passing without touches any obstacles, and shooting accuracy. So as I read the rule books of the RoboCup Future Challenge, I can see the challenge 3 skill test is similar with our rules. The aim of the challenge is like improve their basic soccer skills, work on accuracy. So it's like our challenge and in our country. And the procedure for doing this is also similar with our rules. It's like ball travels, the receiver robot can grab the ball, and the ball and robot doesn't hit or touches any obstacle during the travels, just like our competition. And of course, the ball was kicked from outside the penalty area. So I think this competition is possible to do, and our team has done with it. And this is what my presentation. As Michael Jordan said, talent wins game, but teamwork and intelligence win championship. My name is Budi Satriavi from Iris, Indonesia. Thank you.
Thank you so very much. Any questions? A very interesting report. And I'm not a question, but I really want to invite more teams from your country to next year. Thank you.
Yes, we hope so. We hope so.
I have a question. Is that okay?
Yes, please.
Okay, it's a question of clarification. You have shown that you use an extra camera to validate, let's say, the robot for the pass. Do you also use that to validate the position of the robot? Do you calibrate the position on that? That to me was not clear. Yeah, this front camera.
Okay, so additional camera is used to system control of the robot position before the robot kick the ball to passes to the other robot. And a tag number is attached. It's used for detecting, the camera is used for detecting the tag number using its color, using PID. So before the robot passes the ball, the tag number, the camera and PID control the robot position, and so the robot accuracy will increase before the robot kick the ball for passes to other robots.
So you really measure the location of the number tag before passing?
Yes, correct.
Okay, thank you.
Thank you for your question.
Can I ask one more question?
Yes, please.
What is
please.
Thank you. What is the resolution of your front camera to see number tags from 5-6 meters something?
Beg your pardon, sorry. Can you repeat the question?
Sure. What is the resolution of your front camera to be able to see the number tag from 6-8 meters?
I think Valentin asked the resolution of your camera.
Yes, resolution in a pixel. How many pixels are on the sensor?
How many pixels in the picture?
Yeah.
Okay, so the pixel of the camera is 920 equals to 720.
120. Okay.
Yeah.
And
so it's possible to use in this robot.
And what is to how many meters can you identify the number tag? What is the maximum
Okay, the
distance for
the maximum distance for the camera
for-
detecting the tag number is 6 meters.
6 meters? Okay, thank you
Yes.
very much.
Thank you for your question. Okay, any question more?
I have maybe it's not a question, but I want to ask you. Could you please show me the page of the team list?
Oh yeah, sure. Yeah, it's youngest boy in this competition.
I mean the team list of the 2020 that which show the result of
Oh.
your competition.
Oh yeah. Is that what you mean?
Yeah. So all these teams are all from your country, right?
Yeah. The total of the team that participated in this competition is 36 teams. and
36.
It is, yeah, 36 teams.
Okay. Do you have any information about how many teams can play RoboCup?
Yeah, I guess from now it's 2 teams from Indonesia, Dagozilla from Bandung, Institute Technology Bandung, but suddenly they can't join this competition. I don't know why.
Oh, I see. So I want to see more and more teams to come to middle size, and thank you.
Yeah. Thank you.
Thank you very much. And if you finish your challenge, could you please stop share the screen, and I will share my screen. Thank you.
Okay. Thank you for your attention.
Team member of Iris, could you leave this competition room? Thank you. Next team, Tech United.
We are ready.
Okay, so could you please wait just a few minutes, and I will wait for the team members of Iris leave the competition room. Thank you. Team member of Iris, could you please leave the competition room? Thank you.
Next is Tech United. Tech United, please move to the competition room. Thank you.
Team Tech United, if you are ready, I will stop share my screen.
We are ready.
Now it's your time. Okay, please.
Okay. Hi, everyone. My name is Ense, and I'm going to present to you today the technical challenge of Tech United Eindhoven. It's about shooting effect balls, the road to 2050. Cristiano Ronaldo's free kicks are as famous as their effect. They're fast, accurate, and extremely unpredictable. His success rate during free kicks is about 3 times the average. So what is it about his free kicks that makes them so dangerously unpredictable? Scientists have analyzed his free kick in detail by tracking reflective markers all over his body. To get the ball to curve, Ronaldo must strike it in exactly the right place. This is achieved by hitting the ball off the center of mass. He hits the ball to the side and then uses the inside of his foot to wrap around that ball to generate the spin. Once spin is generated, this creates a pressure difference between the inside of the ball and the outside, and this will tend to push the ball into the direction of the lowest pressure. In total, Ronaldo sends the ball off his trajectory by almost 3 meters. It is this spin that makes Ronaldo's free kick so incredibly difficult to defend. So how can we teach our robots to do the same? That's why today I present to you our research on a novel way of shooting effect balls by making improvements to the robot hardware and software. There are multiple methods of shooting effect balls. We can opt for an approach like Ronaldo did by shooting the ball through the air. The big disadvantage of that is that very high linear and angular velocities are needed. The average human can shoot a free kick around 30 meters per second, but our robots can only shoot at 12 meters per second. In addition, the RoboCup field is a lot smaller than an actual soccer field, which means that by the time the ball deviates from the path, your shot may be long past the goalkeeper. A second option is rolling across the ground. A big disadvantage of this is that it's highly dependent on the friction, how much you can get the path to deviate. Here you can see a few trajectories of the ball for different frictions. The blue line is a billiard ball. You can see because it has very low friction with the ground, it can make a high deviation from the path. Here below, you can see what it would look like if you have a very high friction. The higher the friction, the lesser the curve. So here there's no friction, high friction, so no curve at all. Our soccer ball is somewhere in between, here at this red path. What we want to do today is propose to you a novel approach, which is a combination of these two, that can give us much higher path deviations while requiring smaller angular and linear velocities. We plan on doing this by shooting the ball with a spin, and then at the moment of impact, using a bounce, the path will deviate a lot because the ball is not perfectly straight on the ground. And when it bounces with a spin on the ground, it will deviate. So when will we shoot such effect balls? Well, we will focus on penalties. And I draw for you a situation here in which we will use it. We shoot a ball towards the right side of the goal. And we expect the goalkeeper to move to the right side because it expects the ball to be hit into the corner. In reality, if we shoot the ball with spin, and it will bounce either at place 1 or 2, we can make a high deviation in the path and suddenly have the ball veer to the left. Our hope is that the goalkeeper will be too late to catch on and we will score a goal. So how is this relevant for our league? Well, we've seen some effect balls in our league, but our goal today is to show you that we implemented a new way of shooting effect balls without damaging the ball and also with a higher path deviation, so the other robots that we try to surpass cannot catch up anymore. So what spin and velocities do we need to accomplish this? Well, we took the equations for a 3D ball trajectory and inversed them to calculate the required ball spin and velocity for a range of bounce angles. You can see that in the graph here. The ball is shot, and at the moment of impact, we want different bounce angles to have the ball bounce off in different ways. We solved this problem by minimizing the required spin, as introducing spin is a lot more difficult than reducing or increasing the velocity. So now that we know the velocities that we need, we can calculate where the ball should be hit exactly. This is done by solving the linear and angular momentum balances that you see here on the slide. Here in the image, you can see the front view of a ball. The netto force, F net, on the ball is a combination of the normal force, Fn, which introduces the linear velocity, and the Ft, which is the tangential force, which causes spin. By our calculations, we estimate that for most of the paths you saw on the last slide, we need to hit the ball off center with a deviation of more than 2 centimeters, which is dx. You notice there's dx here. So is our current hardware capable of shooting such balls? Well, there are a few components to this. Our robot has 2 main components for shooting effect balls. We have a ball handling mechanism, which you can see here. There are 2 arms, and they can move up and down to catch the ball. We also have a shooting tip here, which shoots the ball forward. In order to shoot such bouncing effect balls, we need 2 different things. First of all, we need to have the shooting pin hit the ball at an oblique angle, which is not currently possible with our shooting tip. This is because our shooting tip is mounted straight to the robot and it cannot veer off to the side. In addition, we need to hit the ball off center when shooting at the ball. But this is also very difficult for our current mechanism to handle. Here on the right, you can see an image of how much we can deviate the ball from its ball handling. You can see that in X direction, we have a range of about 2 centimeters that we can move the ball. And in the Y direction, we have also about 2.5 centimeters of range. But if you remember, I last showed you that if we try to hit a lot of bouncing balls, we need more than 2 centimeters of play in our ball handling mechanism. So the short answer is no, because we cannot shoot at oblique angles. And we can also not hit the ball off center. So what hardware changes do we need to make to accomplish this? Our idea is to decouple the spin from the linear velocity. Here's a schematic overview of what we plan to do. We have a shooting pin, which we use to shoot straight at the ball and introduce the linear velocity. The ball is placed on 4 ball bearings, so it can move around frictionless. And there's a little wheel on the bottom of the ball, on the top of the ball, to actuate the ball to generate the spin. On the left side, you can see how we plan to actually implement this in the schematic overview in a way that it doesn't obstruct the ball for more than 2/3 of the ball, which is one of the Robocop regulation rules. So we tried to build a test setup to test out our new design for shooting effect balls. You can see it here in the schematic overview. We have the 4 ball casters, which means the ball can move around frictionless. We have a DC motor on the bottom, which can actuate the wheel, which you cannot see in this image. And the other parts, the solenoid, the plunger, and the capacitor, are all parts of a normal shooting mechanism that is used to shoot the ball forwards in a linear direction. On the right, you can see a little bit of a mess, but this is the shooting setup in real life that we built and tested with. So here can you see the test setup in action with the ball shot. You can see that the ball has a spin at the moment of shooting it. It veers off to the left. And at the moment of impact, it veers off to the left even more. And you can see that we placed a marker on the floor at every point of impact. And we did that for a lot of impact points, as you can see in the image over here, with a lot of different settings for the speed and the bounce angle that we want to achieve. So for you, I plotted the results in this graph. In the pink dots, you can see where we actually expected the ball to hit the floor. And the clusters here, the red and the yellow clusters, show where we actually measured where the ball actually hit the floor. You can see 2 different graphs here. They are made with different duty cycles and spins. The duty cycle is correlated to the amount of force that the solenoid uses. So a duty cycle of 100% results in the highest ball velocity that we can generate. And the spin here is around 24 radians per second. And on the right, we have a little bit of a higher duty cycle, but mostly a lot higher of a spin of 35.3 radians per second. You can see that with this, we accomplish deviations of almost a meter, which is quite a lot if you look at the size of a robot in one bounce. So in conclusion, I presented to you today our new design for an effect ball shooting mechanism that doesn't damage the ball and can generate much higher path deviations than we've seen before ever used in the league. And in our future work, we plan to extend this to dynamic gameplay situations because right now all our tests are static. And we also will implement the design in our new generation of robots. Yeah, I hope that we can show them to you on our next tournament together with new robots. Thank you very much for listening. And I'm open for any questions.
Thank you for your presentation. Questions, please.
I have a question, if I may. Angie, you showed the test setup to be completely in the air, and while playing a robot game, the ball will be on the floor before shooting it. Or how does that affect the outcome?
Well, mechanisms when yeah.
Sorry, I can't hear you very clearly. Could you please adjust the microphone? Okay, thank you very much.
Is it better?
Yes, yes, much better. Thank you.
Much better.
Okay, so if you look at this picture, so here you see the test setup, and you indeed see that the ball is in the air, and that is needed to be able to rotate it frictionless. But of course, as Ans already mentioned, the ball, there are some restrictions, so the ball should lie on the ground. And it also should not be held over 1/3 of its surface. And that's actually what you see in this picture here. The left picture is more the representation of how we would implement it in real life. So this is actually a side view of a part of the robot. So here you see the shooting solenoid and the shooting tip. So here the ball is actually on the ground. And those ball casters that Ansel was talking about are not below the ball anymore, but to the side. So this will reduce the friction, hopefully will reduce the friction with the floor enough to give the ball a high enough spin. Does that answer your question?
Thank you. Yeah. Thank you.
I have also a question, if it's possible.
Yes.
Yeah, thanks for your very interesting talk again. This method for spinning the ball is very interesting, but it's a little bit far from real player behavior because, for example, like you said, for Cristiano Ronaldo, when he's shooting a kickoff, ball is static. Before being shooted. Did you investigated the ability of shooting with a rotating arm on plunger and with a rotating system with additional friction, for example, with a kind of rubber that can be inclinated from the straight direction? Because it's another way to do curling effects, which is very different from your solution, which is also interesting. But it's closer to real human playing.
Yeah, of course. If we could shoot the ball like Ronaldo could, that would be ideal. But we're also looking at realistic future implementations within the near future. Of course, Ronaldo hit the ball at an oblique angle with the pin. For us, that's quite difficult, which is why we chose to couple the pin and the linear velocity and the spin generator. But in reality, a solution where you could actually do that in the same mechanism, that would be really cool. Yeah, but the focus of this presentation is something that we can actually build in the near future. Making something like Ronaldo did by shooting it at an oblique angle and then wrapping your foot around is technically a lot different from what we're currently doing. And this is a nice step towards the right direction. And I very much hope that in the future we can do it like Ronaldo does. But this is our down-to-earth robot implementation that we can actually make that will actually work on the robot. Does that answer your question?
Yeah, sure. We greatly wait for seeing it in real conditions in your robot. It will be fantastic.
Cool.
Hello, I have another question, if I may.
Yes?
Question is that, well, according current rule, probably it's not possible to rotate the ball before shooting. I mean, in that case, you will give the opponent team a free kick because the getting the ball, I mean, in the rules clearly mentioned that when the robot's getting the ball, it can stop the ball from natural rotation or direction, something like that. I mean, it's not possible to rotating the ball before shooting. And even for, I mean, making those force to stop the ball, that amount of force is for less than 1 second, and the ball should be on the ground, not off the ground. So if that happened, I mean, probably we need to change the rule. I mean, for every kick, you will get, the opponent will get a free kick in that case.
Yeah, thank you for your input. That's indeed something we have thought about. So you indeed say the ball should lie on the floor. And as you see again in this picture, yeah, this is how we want to change the design to meet all requirements. So indeed, we are allowed to rotate the ball out of the actual direction within 1 second. So that means that, yeah, this conveyor belt or the small wheel that you see here should accelerate to its needed spin within 1 second. And we think that with the wheel we tested now, that is possible. And by putting those ball catchers on the side of the ball instead of below the ball, we hope, yeah, to just keep the ball on the ground.
Okay, so you were, yeah, I think so. You are still getting the ball on the ground, but what about rotation? I mean, if you rotate the ball, the referee can stop the game. Because yes, rotating is not current. It's not possible according to the current rule, at least.
I believe that it's possible for less than a second. So for 1 second, it is possible to rotate the ball. And the wheel that we tested in our test setup, that you saw in your presentation, can generate the required spin within less than a second. So currently we're still within the rules. Probably it's a different, I mean, translation of the rule, because in the current rule it said for any force stop the ball. It's if I just wanted to, it's on page 14, and it said nothing more than that. Just it's more stuff for stopping the ball, not for rotating the ball. Well, but if you wanted to mention use something like this, probably we need to discuss more between theses to consider what will happen. But in my opinion, in the rule, it's clearly mentioned that for stopping the ball, it should be possible, but not for rotating the ball. Okay, we can take a look more sharply at the rules. But, yeah. I think regardless of the rules, it's a very cool concept that we can shoot effect balls with such a high deviation. So, yeah, if that requires a rule change, or we need another way of spinning the ball, for example, turning and shooting during turning or something, yeah, more creative, then that is of course possible in the future. But for now, I think this showcases how much we can accomplish when looking at the Cristiano Ronaldo as our example. And it's also still a quite open design, so it's more basically about we know about the method how to give a certain deviation to a path by inputting a certain velocity and a certain spin, and then how we give that spin and how we give that velocity is quite open. So it's all open for brainstorming. This is also just the first idea. So there are probably more options. Okay. Thank you very much for your good work.
Okay, thank you very much. And if you have finished your challenge, please stop share the screen. Okay, thank you. Next, we will have a VDL. Team VDL, are you ready?
Yes, VDL. So please move to the competition room. Thank you.
Team VDL, can you hear me?
Yes, I can hear you.
Okay, and
Can you hear me?
okay, I see your camera. We still have 2 minutes. Wait a moment. If you are ready, I will stop share my screen and it's your time.
I'm ready.
You can share your screen. Thank you.
Can you see my screen?
Yes.
I'm live, so I can start. Oh, thank you very much.
You can start. Thank you.
Okay, thank you. Welcome everybody to the presentation of VDL Robot Sports. And we focused on a low-cost, fast and mobile object detection for robotic soccer. And why did we do that? Because we are convinced that if we want to win from humans in 2050, we have to have some form of artificial intelligence and adaptive behavior to win. Because if we only want to win with if-then-else statements, humans will always outsmart us. Moreover, there is a big revolution ongoing, and let's bring that revolution, that AI revolution, to RoboCup. We're not the only team; we see it in quite some places. However, we focus on something where we think we can add a lot of value, and that is to bring low cost and fast and mobile object detection to robotic soccer. Because why? Because we want to detect these objects fast, and fast objects, of course, e.g. a ball that's coming towards you quite fast, on the soccer field based on local compute, and it has to be affordable for teams. So we're not Tesla. We don't have a giga data center. We don't have a gigantic bandwidth in the back end to do all kinds of high-tech compute. We want to compute it locally, and we want to do it fast. And we have been able to do so. So next slide, I'll start you a quick video. It is without sound, just don't worry, just look at the images while I do the voiceover. Here you see the result of our work. We detected the ball, the goalpost, humans and robots. And we did so with a YOLO V5 algorithm. So why did we choose YOLO V5? I tested the various methodologies, mobile nets, different robot, let's say, versions of this software. But in the end, we ended up with the version V5 because it was very promising result. YOLO V5 is the 5th generation of YOLO. It's from June 2020, based on convolutional neural networks, state of the art, as I said, very fast, but most important is targeted on mobile devices. In this case, YOLO V5 has a footprint of 15 megabytes, so not 1500 or whatever the number is, and it trains 15 times faster than YOLO V4. So there's some considerable advantages in this YOLO V5 algorithm, and especially in the cloud, it's extremely fast, because what is important for us is it also fast on our local robots with local inference with low latency. We picked, there's several versions of it. We picked the small version, and the results you saw on the previous slide is from the small version. Not bad, I would say. So how did we do it? Here do you see the continuous digital feedback loop? Something that I learned from Tesla. I worked in the automotive industry for a couple of years. So I saw Tesla doing this. I thought, well, that's the best practice. I'm going to copy it. No need to reinvent it. Basically boils down, we have robots with cameras that pick up images. We collect the data. We train, let's say, with the data in the clouds on Google Colab. We deploy it via an O and an X model, and then we optimize for optimal inference, let's say on an NVIDIA TensorRT read and Jetson Nano. So we are able to generate real-time inference on Jetson Nanos, and I think it's pretty amazing. So you have to start with collecting images. We collected 1,000 images and annotated it. To previous speakers, that's quite some work. But we did it. Also credits to ASML because they made a data set available for us to have a quick start. However, we have horizontal pictures and they have vertical orientation. So we used our own set as well. And we annotated everything in VOC XML, which is the standard, the universal standard. And we also made available some software to convert it to YOLO text file format so that you can use it uniform, let's say, for this specific solution for YOLO. The tool set that we used was label IMG, also free of charge. So back to the point of affordable. We made them available not only on GitHub, but also on the Kaggle machine learning environments, because I'm hoping also that a lot of people in the, let's say, machine learning environments are also willing to look at these images and contribute to the robot sports and the robot soccer. In the cloud, we trained it on the free Google Colab GPU. Basically, you submit a Jupyter notebook and you get a free GPU. Again, free of charge. That's why I said low cost and very affordable. And it's moreover, it's very handy. A lot of stuff is pre-installed, so not a lot of pip install, whatever errors, you just can start. You can train the YOLO V5. It has 7 million parameters, not 40 million, only 7 million parameters. Again, the images that we saw before is generated with 7 million parameters. Even 7 million parameters is a lot of parameters to learn. Let's say only with 1,000 images, but it is a form of transfer learning. That means only the last layer you need to train, and a lot of, let's say, work that has been done by the YOLO team you can reuse. And moreover, I can train 300 epochs. The whole video that you saw is trained in 2 hours in the cloud, not 2 days. And I was really surprised about the recall and precision matrices. First I thought, is it now overfitting? Do I see it right? But we tested it in very circumstances, very different circumstances, and wow, it's an amazing recall and precision that I really, really like. So again, some more results, yeah, as mentioned before, partly shielded balls, we see them, different color of balls, we can see them. With our current software, we only detect the yellow ones. Now we see all the different balls. We can very much follow the ball to the picture to the top right, and also different lighting conditions, far better results than our current type of software. But training, let's say YOLO, or YOLO V4, V5, whatever YOLO, I think that's in the meantime some common knowledge. What we needed to add was the capability to deploy it on a local, low-cost, fast inferencing machine. And there, I would like to give the word to Noah, who did some really amazing work. Noah, go ahead.
Yes, so two key technologies that we are using in our solution are ONNX and NVIDIA TensorRT. So ONNX is a machine learning standard in which you can represent your neural network for use in many different AI frameworks and libraries. And we use TensorRT for the inference part. So our approach is basically as following. We train the YOLO V5 network using PyTorch. We convert it to ONNX. And then from the cloud, we distribute this neural network to our robots in ONNX form. And these robots have a Jetson module running, which is running TensorRT. And this last step is really the key to our approach, because you might train some amazing network with great performance, might be very interesting on its own, but if inference takes too long, you can't actually use it in practice. We want to achieve high performance and make everything low cost, low power, and make it actually fit on a robot. And we found that TensorRT is very suitable for this. So we take the ONNX model on the robots and we load it in TensorRT, and then we optimize it for inference. And the result of this is an inference engine, which is optimized for the specific device you're using for your object detection. Might be a Jetson Nano, it might be some GPU. It supports most of the NVIDIA devices. Well, and currently we've managed to get this working at about 25 to 30 FPS on the Jetson Nano. but we have already identified several aspects which could push this frame rate even higher. Well, and so far I'm talking about soccer robots because that's what we're here for after all. But the same approach can actually also be applied in, let's say, industrial settings. Finally, I will mention that we will make all of our code available on GitHub so that everyone can use it. So like I just mentioned, the hardware that we're using is the Jetson Nano from NVIDIA. Also we've used the Stereolabs Z2. So the Jetson Nano is part of the Jetson lineup of mobile solutions at NVIDIA, and it is specifically intended for these machine learning workloads. They can be obtained for a relatively low cost. They don't use much power. They're very small, and they deliver great performance for its small form factor. There's also higher end Jetson variants. I think some teams mentioned this yesterday, and these perform even better. And our software is also compatible with those, but those are more expensive. So we decided to go for the Jetson Nano. And for the actual imaging, we are using the Z2, which is installed on the VDL Robot Sports robots. And this is essentially because of our future ambitions. We like it because it uses passive stereo depth technology. It doesn't cause interference, like let's say the Kinect. And also it works very well in outside environments. But in principle, everything we've described so far with YOLO V5, with the Jetson Nano, with TensorRT, would work fine with cheaper camera models as well. Let's say a webcam. You don't need stereo depth for the object detection. Now my teammate, Cheryl, will continue.
Yeah, so I would like to conclude. We bring to you state-of-the-art AI, the latest versions on 25 frames per second on a low-cost module or with approximately 50 milliseconds of latency, which is of interest for the whole league because it's amazing to get this type of, let's say, real-time precision and recall for objects on the soccer field. E.g., you saw the examples, field ball, different colors, different lighting conditions. Moreover, 2 hours training means that I can train it during the setup day. So when I do the setup, I make some photos, let's say multiply them a little bit in the sense of rotate them and optimize them and different lighting conditions, whatever we want. And then we train in 2 hours and we have a fully loaded data set that we can even, let's say, make targeted for the local circumstances if needed. We needed to solve a vast complexity, 2,000 lines of code. So I hope you notice it, it's countless hours, but that was needed because also, let's say, the AI world is quite a jungle out there. So we need to sort out how you move from YOLO V5 into ONNX, into the TensorRT, and then optimize it for this low-cost hardware. But we sorted it out and we make it for everybody available. Because with that, with a $99 unit and a simple camera, every team can start with quite some robust object detection on the robots. So that gives a lot of acceleration possibilities for all the teams. It's affordable for all. Again, I can't stress it enough. And it's based on open standards. Also thanks to the French teams who in the workshop pointed out to me the ONNX standards. We immediately jumped on it, sorted it out, embraced it. Very good. Vox XML standards, I think is also a good one. And yeah, you see the videos. And please check it out. Please check our website, etc. So. With that, I only need to conclude. Here you see a picture where it is mounted on our newest robots. We're building and prepping that robot for being, let's say, when we're allowed again to meet face to face and have some actual competitions. You will see this robot, which is fully equipped with artificial intelligence object detection. And I hope a lot of people will take the benefits of this approach and have some very robust detection, very affordable on a mobile base. Thank you very much.
Thank you very much. And questions, please.
Yes, one question if it's possible. Thanks for this very interesting talk. You said that you are planning or are you already testing to use stereo vision on your robot?
We're testing, so it's not needed for this application that I just showed, right? So this you can do without that camera. You can do it with a very simple camera to have low costs. Hence, I didn't pitch it too much. But yes, we are also testing this and trying it out to do depth detection, especially when you have balls coming in through the air. For example, for the keeper extension to launch is a very simple use case where we are looking at.
Okay. And with stereo vision, are there enough power in Jensen Nano?
Yes. Go ahead, Noah.
Yes, so the Z2 that we've shown on the pictures, I believe it uses about 2 or 3 watts, and the Jetson Nano can handle it fine. So we haven't had any issues with it.
Oh, I wanted to say computing power, not.
Oh, computing power. All right. Yes. So this was really we spent a lot of time trying to get this to work, but with the lowest settings, like the lowest resolution, which is 672 by 376. We can run the Z2 at about 60 frames per second, but that's still without any neural networks and without any AI.
Okay.
So what we really focus is to get it on a low cost machine. So yeah, we can always upgrade, right? We can just spend more and get higher versions of NVIDIA stuff, not a problem. But the real effort went into to make this affordable for everybody, because 5 robots or 11 robots on the field, 5 times the cost. Let's put it that way. So we try to really get to the next level to get the most out of it, even out of a $99, let's say, AI edge device.
Thank you very much.
I have a question. First of all, I want to say, it was a really fantastic presentation of work, and especially when it's published online and it's open source, it's really good. And also I want to ask your team and also the other teams, if possible, to share PowerPoints. In that case, I can publish them on the website, Middle-Size League website, so everyone can use those links and your work, and it will be good for the league. And so my question is about the as you mentioned that you didn't use the stereo camera, just use the 2D camera for object detection. Did you check different backgrounds? For example, in normal case, in competition, considering a kid out in audience carrying a ball or a balloon, what will happen in that situation when there's a different background on the around the field, let's say? Because you don't use the 3D, so you don't know what is the distance to that object to remove those objects outside of the field. What will happen in that situation?
Yeah. Well, first of all, thank you for the feedback, much appreciated, and absolutely will make sure that the slides become available for everybody, not an issue. And yes, we were also, due to Corona, a little bit handicapped moving around to different fields in the world to get all the images. But let's say I've seen enough of machine learning and artificial intelligence and YOLO results that I'm very confident that the background will not be an issue. We will sort it out. Worst case is that I need simply more training material, read another 1,000 images to get it sorted out. But I would love to have said, yes, I've been in all the fields, but yeah, we couldn't travel. So this is the best answer I can give at this moment.
Thank you very much.
Thank you very much. If no more questions, could you please stop share the screen?
Yep, thank you.
And the next team, Robot Club Toulon, France. Team RCT, are you ready?
Yes, we're ready.
Okay. Now I will stop. We still have several minutes. First, I will. Okay, I stop share my screen, and you can start according to you. It's according to you.
Is it okay?
Oh, yes, it's okay. And
I just have to change. Sorry. Oh, I'm sorry.
okay, if you are ready, you can start your presentation. Thank you.
Just 1 minute. Okay. Okay, thank you very much. Thank you very much for attending this RoboCup scientific challenge. For our team, we will present how to play with humans on a special point, improving embedded perception. Like I said yesterday when introducing playing with humans from other point of view, when we see a football game, we never hear players saying, okay, I'm at this position and my action is that action, and the other position I can find are that, all that. So as I told yesterday, playing with humans raises major challenges. First one is playing without wireless communication. I explained it in technical challenge. Second one is improving robot skills. And also it has been presented in technical challenge. But playing without wireless communication requires a third point, improving drastically embedded perception. Because there is no more shared perception. And each robot have to make identification and localization of robots, humans, landmarks, referee, all with, like VDL said before, limited hardware computational capabilities. So how to do that? First, what is an improved perception? As we can see here, we have to first identify who is around the robot: players, opponents, referees, landmarks such as a goal here. Then what are their position? Okay, they are at 5 meters from me, they are in a certain area. It's the same for teammates, opponents, referee, landmarks. And also something very interesting presented in the excellent technology talk yesterday. What are players doing? This is mostly postural communication. This is told by gesture of teammates, opponent, referee, coach again. I will not focus on this later point here. How to do so? First, let's explain how it is done for humans. First, there is a vision preprocessing in human cortex here from the retina, and then question who, what, and where are answered by two different brain channels. First one is cortex ventral pathway for identification and posture for who, what, mainly based on vision. And second one is the cortex dorsal pathway, coupling sensor, vision, stereo vision, or acoustic perception also. This is the key bio-inspired idea of this scientific talk, to make a complementary perception organs with parallel processing. This is what we will implement in robots. Combining multiple sensor and processing is the key for playing with humans for us. So we will combine several sensors. First one is LiDAR. Because of its precision, angular and radial, but only 1D and no perception of color. Second one is camera. It's 2D, with color, but no radial precision. And third thing is the processing. It's SLAM for sensor fusion. This is represented here. Our first contribution is a technical contribution. We have made a change to the who-what question with a new omnidirectional camera. New technical choice because we have removed the omnidirectional mirror, replacing it by here 155-degree fisheye pointed vertically to the ground. This is important because there is no need for hardware calibration of the mirror to have the same axis of alignment, an excellent optical quality. And then we transform the image to panorama, like here. Here you have the image on our field, and here the panorama image with 360 degrees. And the software auto calibration instead of hardware calibration, so it's much more simple. We just have to find the fisheye center to have a straight panorama image here. This is our first contribution. Sorry. Then, then we have decided to implement also YOLO V5 algorithm on cameras, and this is our second contribution. We have implemented it to unwarped spherical images. This is the YOLO model. It's like a VDL said implemented in ONNX also. And but it's a little bit different from standard images because, as you can see, there are very I launch it again. There are very curly lines here and many distortions. So we trained it using new boat training set with additional fisheye panorama samples. It gives a very good result with an area under the curve of 87% for goal, robots, ball, humans. A latency, not really real time, using YOLO V5 large model 25 FPS, YOLO small model more than 60 FPS with a GPU use of 6%, CPU use of 20%, mainly for fisheye to panorama. This shows that we are able to segment complex scene, distinguish human colors. An idea would be to extend the size of the shirt for easier analysis later. An excellent angular resolution, but there is a very poor radial resolution and it's computationally expensive. So to answer the question, where are players, where are goals, where are opponents, we have decided to add a LiDAR. This is our LiDAR, this is our Omni camera. LiDAR is a perfect complement to Omni camera. It has an excellent radial resolution all around the robot of less than 1 centimeter, 360 degrees. That is difficult with stereo vision if we want to get some, because stereo vision is another option. And it allows landmarks extraction with precision. For example, this is a video taken from this robot in a large field. As you can see, we can see players moving here, and the robot is here. And we try to find the boundaries of the room by geometric techniques. We can see that it's working, but if the scene is complex, it's a scene just taken picture just before it's a classroom, more robust processing are necessary. So what are this more robust processing? We have designed a really novel algorithm, I think, because we didn't find anything like this in the literature. It's a low computational cost 1D LiDAR deep learning algorithm. That means this is the data from the LiDAR in 1D. This is the equivalent figure of the room taken from as a 2D map, but the only signal is 1D. As you can see, it's a very difficult map with tables and chairs everywhere. And what we want to find is goalpost from the scene and corner of the room. It could be found with 2D image analysis using CNL, but it's computationally expensive. So we have decided to focus and to try to do it only using 1D signal. We have used a dedicated labeling software. Of course, it cannot be done by standard tools. We use a custom 2-layer CNN. It's a very, very small CNN, actually, optimized for, this is a loss function, object angle, distance, and classification results. Results are very, very nice, as you can see there. We have an array under the curve, which is 85%, so it's good detection. As you can see, even on very difficult configurations, it's still working properly. It allows an efficient positioning with an efficiency. Radial standard error deviation is less than 10 centimeter. Angular error standard deviation is less than 1.5 degree. And most of all, and this is most important part, a low computational time, less than 1 millisecond, allowing a low latency and allowing to make several processing in parallel. What is important in that, the final perception step, we have to merge data in a single world map. This is done using standard extending Kalman filter, simultaneous location on mapping. But for this, we have to have reliable landmarks. This is why we have done the preceding steps. I will present how Tim will present it more deeply next year. I think it's too short. So finally, in conclusion, play with humans requires improving embedded perception. We propose in this talk a bio-inspired combination of sensors and efficient processing with 3 contributions. First one is an Omnicam with a software calibration only. Second one is an application of Yellow V5 to unwarp spherical images. It hasn't been done, we didn't find it before. And third one is the most important because it replies to the question who, what, where, with a low power. It's a low computational cost 1D LiDAR deep learning algorithm. Everything is shared on GitHub at this address, and here is a list of recent publication, 3 articles on 2 conferences on the last 2 years published related to RoboCup MSL and multi-agent perception. Thank you for your attention. If you have any questions.
Thank you for your presentation. Questions?
I would like also to thank all my team because they are around and they have made a fantastic work.
Okay, thank you. Any questions, please? So any questions, please? Questions, please.
Well, I have a question. First, again, thanks for your presentation and well, really nice work. I want to know that did you use the LiDAR for? I mean, 1D. It was what kind of LiDAR? What was? I mean, the LiDAR. It was a 3D or 2D LiDAR. I didn't get that part. What is the specification of the LiDAR that you used, and also what is the if you used it with the camera, it was with the omnidirectional camera, or it was another camera, extended camera you added to the robot?
For the LiDAR, it's a standard 1D, it's a standard planar LiDAR. Like you can see the signal here and the corresponding 2D map here, but it's a single in only one plane. We don't have 3D information, it's too expensive. And for the camera, we can see it there. It's a standard Basler camera with a good resolution, but due to the fisheye, we use it only on a small part of the image, about 800 pixels by 800 pixels. Because of course there are many black areas on the image. There is one trick on the camera. If someone wants to do so, you should try to find a good resolution camera because it requires a large sensor. because if we don't have a large sensor, it was the case with the previous camera we had. There are some image. I will show you. No, not there. Sorry. Yeah, before. Yeah, before there, if the sensor size is too small, image is truncated, and it's difficult to use it after because most of the information is in the external circle of the camera.
Thank you very much. So if we use only the LiDAR for detecting objects, how you distinguish between, what is the difference between, for example, a robot that is stable and the goal? For example, if the goal is not moving, how you will detect it as the opponent?
Now, to focus on the perception scheme, the perception scheme is described here. We have the camera here, the LiDAR then, and then we have landmark extraction by conventional and CNN techniques presented. We have object detection from the camera using CNN techniques here, and also conventional object detection using LiDAR. And after, object detection from LiDAR and object detection from camera are merged in an environment analysis tool, and also landmarks detected by camera, landmarks detected by LiDAR, and odometry and inertial measurement units such as gyro or accelerometer are merged using simultaneous location and mapping here. This gives an absolute position and a scene description, and environment analysis tells that objects found are ball, teammates, opponents, referees, etc. And all is feeding the World Map Manager here. Maybe it's clear. So we are using both, of course, camera and LiDAR to find objects. I think it's really necessary because a camera is very interesting for finding objects, like several teams are presented, but positioning is not accurate. It is not accurate at all because of image projection. With LiDAR, we add very precise accuracy on object detection, and also it's possible to make positioning without using the field lines. This is important because when we will move to bigger fields, in real condition, players don't use lines for positioning. They use goals, they use posts, they use the stadium also for positioning. We do so as explained in the talk, but we don't use, we no more use the lines for position.
Thank you very much.
You're welcome.
Can I ask a question?
Sure.
What is different of the 1D and the 2D LiDAR? 1D means a line, one line.
Yes. In 1D LiDAR, there is just an horizontal plane which is swept by the LiDAR. If you have a 2D LiDAR, or some people say that it's a 3D LiDAR also, but the sweeping plane can be tilted so that you can sweep like this, then like this, then like this, then like this. So you have a kind of 3D map around your LiDAR, but it's much more expensive, and I think it's too much for a robot. We want to focus on cheap solution, like VDL said.
So you use the 1D LiDAR and it's turn, right?
Yes. We use a good LiDAR, a good 1D LiDAR, which has been given to us by our sponsor, Pepper and Fox.
Okay, so you can get the 2D image, 2D mapping, right?
Yes, we have a 2D mapping, but not 3D. But with a complement of camera, it's okay to get a full map of a full world map around the robot.
Oh, thank you very much.
You're welcome.
Okay, thank you very much for your presentation, and the questions is also very good. And if you finish your presentation, could you please stop share the screen?
Thank you very much.
You're welcome.
Last is Nubot, so please move to the competition room. Thank you.
So team member of RCT, could you please leave this competition room? Thank you. Team Newbert, are you ready?
Please wait a moment.
Yes.
Huh? Yes, or wait.
Okay. I'm ready.
So Team Newbert, I will stop share my screen, and it's your time.
Okay. Hello, everyone. I'm a member of the Newbot. It's my pleasure to represent our team to share the work. The title of the presentation is Brain-Computer Interface for Human Multi-Robot Strategic Consistence with a Differential World Model. The corresponding paper is listed at the bottom of the screen. In the middle-sized lake, the world model maintained by each robot is inconsistent, partly due to the measurement errors from the sensors, which will produce different and even incorrect strategies. An opinion dynamics model is used to find the consistent multi-robot strategy, which is not necessarily the best choice due to the inaccurate world model. To make the strategy more reasonable, the human opinion is introduced in our work. Humans have a wealth of priori knowledge and a more global view. When the humans receive the strategy from the robots, humans can accept or reject it and reselect the strategy using a brain-computer interface. Of course, human judgments may be incorrect, and the BCI has false detections. Thus, the robots don't directly accept the human strategy, but add it to the opinion dynamics model as a new node and recalculate the final consistent strategy. The following 4 sections will be presented. First, let's look at the overall flow. In the context of highly dynamic software robots computations, when our robots regain or lose the ball, the multi-robot system needs to choose a new strategy. The robots need to respond quickly according to the situation on the field and provide a consistent recommended strategy to the human. The human can accept or reject the recommended strategy according to their inference. If the human rejects it, human needs to use the BCI to reselect the strategy. Then the choices of the human and the robots are combined to obtain a final consistent strategy. Next section, let's describe how the multi-robot strategy is generated. As is known, all sensors have measurement errors and even false detections. In our study, both the robot self-localization and the recognition of opponents are based. That causes the differential world model for each robot. So the different robots can distinct strategies on differential world models. Strategies are divided into offensive and defensive strategies. The former strategies, while the latter contain the zone marking and the focus strategy. A single robot infers the opponent's strategy from the opponent's robot's positions and then determine the probability distribution of the opponent's strategy. When the opponent's strategy is clear, our robots will make a reasonable strategy. The probabilities are respectively recorded as I point out. The following is an example of defense strategy generation. The strategy is iterated according to the site period until it converges and obtains the consistency. In our study, a robot's opinion is a vector of 3 dimensions, which is conveniently represented by the probability distribution. Superscripts represent different strategies. Subscripts represent robot numbers, and numbers in the parentheses represent the count of iterations. The process of how the strategy is iterated is described as below. The individual strategy selection stands for a robot's cognition towards the environment, which is expressed as the opinion of a robot. Mathematically, opinions are vectors made up of probabilities mentioned above. To obtain the consistency, the opinion dynamics models has been proven to be both effective and powerful. Here, we use the French deGroote model to find the consistent strategy for the multi-robot system. The key parameter of this model is a random 4x4 matrix of consistent of influence weights. Giving a positive influence weight to each means that the robot is able to influence the robots at each step of the opinion iteration. The greater the weight, the stronger the influence. Suppose that all robots are homogeneous, so the initial value of the influence weight matrix is shown as follows. Greater values on the diagonal indicate that the robot believes more in its own opinion. The following section describes how the human is involved in the generation of the strategies. The consistent strategy of multi-robot system is submitted to the human as a recommended strategy. If the multi-robot system detects that the human accepts the recommended strategy, it will execute the decision. If the human rejects the recommended strategy from the multi-robot system, human can reselect the strategy through the BCI. Based on the strength of the collected signals, it's also possible to obtain the probability distribution of the human thoughts about the opponent's strategy. We also apply the French deGroote model to interact the strategy and obtain the consistency. The gray boxes represent the joint human opinions and the weights of human influence on the robot. There is the initial value of the weight matrix after adding the human opinion. The value in the fifth column is significantly greater than the other values. This indicates that the opinion of human occupies an important position in the initial influence weights. We developed a specific simulation system for the experiments, which is composed of a brain AMP DC amplifier, a graphical user interface based on Qt, as shown in the left figure, and the multi-robot simulation environment based on Gazebo, as shown in the right figure. Here is a video showing the process of our experiments.
Do you want to play a video?
Yes, we are just face some problem. Please wait for a second.
This is a demo video of our work.
I'm sorry, did you play your video? It's very, oh yes.
This is a demo video of our work. Now the experimental environment is initializing in Gazebo. The black robots represent our players, and the red robots represent the opponent players. The GUI for the human subjects is on the left, where they can choose strategies through the BCI. On the top of the video, we show all the options for the human subject. This is a situation where the opponent is attacking. The focused defensive strategy is recommended by multi-robot autonomously. Then the human subject accepts this strategy, and the focus strategy is executed. This is another situation where the opponent is defending. The conservative offensive strategy is recommended by the multi-robot autonomously. Then the human subject refuses this strategy. After reaching the human multi-robot strategy consensus, the balanced defensive strategy is executed. Next, we demonstrate how the human subject can control a single robot through BCI. Firstly, the human subject selects the single robot control mode, and then selects the controlled robot and its specific action. In the video, the human subject replaces robot 4 with robot 5. This is a demo video of our work. Now the experimental environment.
To illustrate the advantage of the human multi-robot strategy, the correct rates of different strategies are calculated as shown in the figure. The six sub-figures represent the experimental results of 6 different subjects. Multi-robot strategies is marked as SRS, which is in blue lines, and human multi-robot strategy is marked as SHR, use yellow lines, and the human strategy is marked as SH, use the orange line. Our first observation is that human participation has a positive influence on multi-robot control, which makes SHR significantly higher than SRS when the robots independently make decisions. In addition, the performance of SHR is robust. Even when the correct rate of the human is not high, it can obtain better results. We argue that this approach has some advantages. First is conducive to the stability of the system. For example, the human multi-robot strategy is less affected by the human's weak performance. Second, the professional requirements for the human are reduced. Even people who is not familiar with the software robots can use this system. Third, the approach can reduce the operator's mental burden, eliminate the need to maintain a high degree of concentration, and avoid the final strategy errors caused by the fatigue. This approach is not limited to the software robots computation. Its feature is very useful for control applications where human operator is proven to make mistakes. Thanks for the attention. Here is the question and answer session.
Thank you. Thank you very much. Questions, please.
So I have a question. So this is Tom Pijnenburg. So in your research, the human collaborates with the autonomous system to make a selection for a strategy. And in your last comparison, you show that this is better. The question is the system learning from this collaboration with the human, and does the autonomous strategy improve based on this?
Okay, the system actually not learn from the human. It's just something like the combination of the strategies. Use this model introduced before. Here, the system just combining the human strategy and the robot strategies. Use the French Degroote model, and this model can make the system learn from human.
So the system can be made to learn from the human supported decisions.
Yeah.
Okay. In the graphs you show on the comparison on your last slide, or last but one slide, on the vertical axis it says, I don't remember quite. So the last slide with the comparison of the 6 situations. 6 subjects, yeah. So the vertical axis is correct rate. What does that mean?
We have a reward for each strategy. It's compared with the highest reward strategy. This strategy is obtained in the before, because we have because we just introduced before, in the real simulations, all the robots have sensor measurement errors, but in the highest rewards strategy, we assume that the sensors have no errors because we know all the positions of the openness robots and all the informations on the ground. That makes the correct rate.
Okay, thank you.
I have a question. First, thanks for your nice, it was a really good presentation and work. My question is that, how did you, a human will inform that robots to change this strategy? If you use a simulation or on real robots, how it will happen? For the current rules, we have the idea to change the strategy or communicate with the robots with gesture detection, for example, using hand or something like that, but for a specific area. I just want to know that did you just use a simulation or also use that in real robots?
Okay. We just use it in the simulation, but to let the system know when the human wants to change the strategy is the human make some motions that make their brain signals change, and we can detect this change and let the system know the human rejects or receive this strategy from the multi-robot system, and next step, we are going to put it on the real robot. Actually, we just put it on. We have just small some work about this, and I can show you a video about this.
Sure, thank you very much. Well, as Tom just mentioned, that if you use those feedback from the human to change the strategy, and if robots learns, well, that's really fantastic at the end, because if in that case, for example, robot will learn from the human, and they, for example, for second half they will play better than the first half. That's what we are looking for in RoboCup at the end. So if you for your future work, if you try to learn from that data, it would be really. Thanks.
This is a demo work of our work on the real robots. You can say it. Okay, please wait for a second. Okay. Oh, there. Okay, this is a demo video of our work applied on the real robots. This is the robot system want to involved in a fire fire rescue work and the firefighting task, and the human from now on the human is involved in the system, and then wait for a second, we can see how the humans change the robot's strategy. Now it's just a robot's strategy. Now human evolved and gave the robots different strategy. Okay. Okay, the video is over. Any questions?
I think time is up. Thank you very much. Thank you, Team Newbook.
Okay. Okay.
So thank you very much. Thank all the team leaders and the team members to give a very interesting and exciting presentations for our scientific challenge. So from now, we suggest we have we use 15 minutes. Okay, 15 minutes to give the score, final score to the all the teams. So just the same as yesterday, if you could edit the Google Driver files, you can directly give the number, give the point in the score table. If you cannot, I have already sent the table to you, and could you please send the table back to me after you get the final result? Okay, thank you for today, and we still have to wait for the final result, and we from now on 15 minutes. Thank you.
One remark, if that's possible.
Yes.
Okay. I'm live editing in the document, so I will give you a note when I'm done. Is that okay?
No.
Or will you? No, I am live editing in the Google Doc. So we consider it ready after 15 minutes, right? Okay.
So after, please, Valentin.
Yeah. I'm still changing the scores that are in the Google Docs at the moment.
Yes. 15 minutes means after 15 minutes, I will change the authority of the Google Drive file. You can only view, but you cannot edit again.
Okay. Yeah. Thank you.
You're welcome.
Just one more question,
please. Yeah.
What do we evaluate in relevance of published results presented as part of the challenge? Are there publications in conference on the papers?
We have already get the points from the result of qualification. So your question is about the, according to the rules, we need the point of
No, it's the last column before some relevance of published results presented as a support for this challenge.
Published and the result.
Not the last column, but before the last column.
So I think this table is almost the same as totally same as we used before. So I think it's up to you.
Okay.
Yeah, and probably there's maybe need more time to find it's really relevant or not to read papers. Yeah.
Yeah, because it's difficult because not all the team have published papers, so it's difficult to answer that.
We have so Axon, do we have a list of paper published in the website?
Teams have these things on their qualification material, and if they are already there. But the question is if they use that on their presentation, probably that means those papers are more relevant to their work.
Okay.
But it's up to team leaders to make their scoring. Yeah.
Yes, it's up to
it's difficult.
It's up to the team leaders. Thank you.
It's very difficult. Okay, thank you very much.
And up to now, we have finished the challenge. So we'll stop the new broadcast and thank you everyone. Good morning, good night, good morning, good afternoon, maybe good evening. Thank you again.